Hello everyone and welcome to this video. Today we will talk about the physical properties of group 2. So firstly, group 2 is also known as alkaline earth metals, and the reason behind this name is that they form alkaline solution when dissolved in water. So if I looked at magnesium, one example of group 2 elements, it dissolves in water, it gives me magnesium hydroxide, which have a basic character. Looking down group 2 elements, moving from beryllium, magnesium, calcium, strontium, barium, you could see that all of them, I have the s orbital filled with 2 electrons, where I'm just increasing the shell number down the group. Now, the metallic radius trend of group 2. Before starting the metallic radius of group 2, we will look at the definition of metallic radius. Metallic radius is usually the radius that we take for metals, and in giant metallic lattice, half the distance between 2 nuclei will be my metallic radius. So if I have here 2 nuclei, in metallic radius are adjacent in metallic radius, half this distance will be my metallic radius. Now, usually in the metallic lattice, you have the metal ions surrounded by the valence electrons. You could see that the metal ions are swimming in a sea of delocalized electrons. This will give a high electric conductivity for group 2 elements. Also, they will have a high thermal conductivity as well. Now, moving to the metallic radius trend down the group 2, you could see that I'm increasing the atomic radius, and the reason behind that, because moving down the group, I'm increasing the number of shells. So in here I have the second shell, and valence electrons are located in the second shell. In here I'm increasing the third, then the fourth. So I'm increasing the distance between the positive nucleus and the valence electrons, and this will just decrease the attraction between the positive nucleus and the valence electrons, leading to the increase in the atomic radius. In here I have the metallic radius values, and you could see it just increased down the group. Now, for melting points and density trends across down group 2, you could see that I'm increasing the atomic number, so so usually you expect the melting points to decrease, and the density will just increase because I'm increasing the size of my my atoms, and this size will lead to a higher density. Now, if I looked at the melting points, you could see some irregularity, and the reason behind that is the packing or the arrangement of atoms in the crystal. So I have 3 types of packing in crystals. The first one is the face-centered cubic, and the second is the body-centered cubic, and the third one is the hexagonal closed pack. The ductility is actually decreased from the FCC to the BCC, and I have the HCB is actually brittle. Now, you could see that in here, if I'm decreasing the ductility, I'm also decreasing the melting points. Now, if I moved at the crystal lattice of beryllium, you could see that it is a hexagonal closed pact at room temperature. Also, magnesium is a hexagonal closed pact, where in case of calcium, you have a face-centered cubic. So the face-centered cubic usually have higher melting points than the HCB, like we said before. So in here, I have decreasing in the ductility. I have also decreasing in the melting point. So I expect the FCC to have a higher melting point than the HCP, and this is actually what happens because calcium here is face-centered. This is why it have a higher melting point than in case of magnesium, which is actually a hexagonal closed pact. And if we further try to interpret the reason behind the higher melting point of beryllium, this is because the small metallic radius of beryllium, because it's very small, it is very the packing is just close together, and this will give it a higher melting point. Now, if I moved to the density trends, also the irregularity in the density trends, so I expect them, it should have been, all of them are increasing in the density down the group, but I have this drop with calcium, and the reason behind that, it is because calcium has a face-centered cubic crystal lattice, which includes only 14 atoms. Where I have, in case of beryllium and magnesium, they are HCB, which means I have 19 atoms included in my lattice. So the higher the atoms in my lattice, this means I have a higher density. This is why in that case I will have beryllium and magnesium will have a higher density than in case of calcium. By that, we came to the end of the first part in the physical properties of group 2. Next part, we will talk about reactions of group 2 elements. Until next video, thank you and goodbye.